Hey guys, this is going to be our, 1.1 and 1.2 change in tandem day 2 notes. And so you're going to see me gloss over quite a bit of this. And well, I think it's fairly straightforward. That's why. And so you want to take time to write down some of the notes that I already have filled in. Feel free to do so. But I'm kind of just going to go ahead and just kind of talk through this beginning part here of why I pretty much filled in uh, this space the way I did. Let me highlight so you know what I'm trying to say. Where is it? There we go. Right, this portion right here. So what I did was fill out this table, and the way I found these values was just finding the average rate of change between the 2 points. So for example, at least just point out the first one so you know what I'm talking about. So the way I got negative 5 halves was by looking at the 2 points A and B, which I'll point at them right now. And I simply just did rise over run, right? You can either start at point A and just go down 1, 2, 3, 4, 5. And since it's going in a negative direction, I'll say it's negative 5. And then I'll go to this point, and that's a positive 2. So negative 5 halves is my slope between those 2 points. And we pretty much did that for all the points that they provided to us, right? A to B, B to C, C to D, so on and so forth until we found all the slopes. And so based on that, we were able to essentially determine the following fact at the bottom here that we claim, right? We claim that the graph is concave up on the intervals A to H because the average rate of change is increasing, right? So let's explain why. I think graphically, visibly, it's for sure going up, right? It's pointing, I mean, it's shaped like this, right? It's definitely concave up inherently, right? Just looking at it. But the reason that they provided was, well, because from intervals A to H, right, intervals A to H, it's concave up because the average rate of change is increasing. And that's true, okay, for any case where the average rate of change is increasing. And you can visibly see this based on the table that we filled out here, right? You can slowly see that the values are getting larger, right? We start off negative, right off the bat from A to B, and at the end we end up being positive. So the average rate of change is increasing, right, since it became positive. So if you ever see it in table form that your average rate of change is increasing, you can claim already without the graph, without seeing it, that it's concave up, right? Simply just a fact, okay? So either you can visibly see that it's concave up, or you're provided a table and you have this reasoning behind it where the average rate of change is increasing, you claim the graph is concave up. Hopefully that makes sense. Then we'll see an example where, well, the graph is definitely concave down, right? I mean, frown down, right? That sort of deal. And so we even fill out the table once more. And as you examine, I mean, you might want to write this down, right? Or you can just simply look, right? You can examine that the average rate of change are currently decreasing, right? We start off positive with this positive 5 halves, which is 2.5. And we go all the way down to negative 7 halves, which is, if I'm not mistaken, negative 3.5. Right? And so if it's decreasing, we can instantly claim that, well, the graph must be concave down due to the fact that the average rate of change is decreasing, right? Those are just facts. I'll let you have a little screen grab here in case you need to write this down so you can pause, but I'm simply going to just move forward now. All right, this is some key facts here. Well, for the most part, these were inherent facts that you kind of already just done naturally, right? They kind of just wrote this out in mathematical jargon, right? So as far as an increasing graph goes, it says that as the input values increase, the output values always increase. If A is less than B, then f of A is less than f of B. Essentially what it's saying is, well, as your x values increase, right? As our x values increase from 1 to 2 to 3 to 4, right? The graph, or perhaps the output for each of those inputs are getting larger, right? When we put in 1, we got 1 back, right? That's where the graph is. We have an input of 2, we get, what is that, 1.5, just about, right? It's getting larger. So as your x values get larger, your y values also get larger. So that's an increasing graph. You already knew that inherently, though, right? And vice versa when it comes to decreasing graphs, right? As x gets smaller, or sorry, larger, in this case, our y values, our outputs will be decreasing, right? That's essentially what this math statement is saying here, right? We're saying that as a is less than b, then f of a is greater than f of b, right? As a gets larger, um, then our y values are getting smaller, right? That's what they're saying. And we just went over concave up and concave down, those rules prior already. So we can simply just kind of move straight forward into the next screen grab here, right? So this is actually our first problem, right? They're asking us a lot of different things here. Um, they're asking us to determine the following behaviors and characteristics for a lot of different things based on this graph, right? So we'll start with the first part of this, right? It's asking us which part of this is increasing. So as far as I can tell, that's usually things with like a positive slope generally, right? Or things going from left to right, but as the x values get bigger, so are the y values. And so I'll start highlighting those locations, all right? So maybe perhaps I'll do this one in green. So let me make my highlighter tool just slightly smaller. So I think from here, from -2 all the way to an x value of 0, this whole entire section that I'm highlighting is increasing from left to right, right? We always interpret the graph from left to right. And so from -2 to 0, let's write that down. -2 to 0. Ooh, let me fix this. When it comes to writing um, increasing intervals, we want to write it in parentheses. So -2 to 0. That's just a convention. As far as decreasing goes, let's see, right? I kind of erased the other portion. Let me just bring it back. Let's say I was highlighting the decreasing portion in pink, right? That's wherever we have perhaps a negative slope that we see, or in the way that they described it in their definition here, as the x values get bigger, the y values are getting smaller. And so I can instantly see that on this left-hand side of the graph here. I can also see that on this section right here as well. Well, honestly, I should keep highlighting more, right? It keeps happening all the way down here. So I have two highlighted portions in which I'll write two different intervals in my answer. And so I should be writing, let's put it in pink. Let's do the first section, right? That's from -4, right? The left-hand side there, -4 to -2, union. Now I'm gonna do that middle section that I have highlighted, right? That starts at 0 all the way to 4. All right, there's my decreasing interval. Now, as far as concave up, right, we're looking for areas that look like this, like where it's smiling, basically, right? And there's two sections. Well, actually, I lied. One section. It looks like two, but honestly, it's just one, right? Simply just this portion here that I'm highlighting in blue. Oop, I'm not highlighting. I will be highlighting now. Highlighting in blue here, right? This is the section where we are considered to be concave up, right? I'm not going to include this piece here just because that section is definitely concave down. So I'm going to say from the concave up, the thing I've highlighted in blue, that starts to happen right at 2 all the way to 7. And then the concave down part, this green and pinkish area. If you watch, what is it, Fairly Odd Parents, I guess this is the fairies here, right? Green and pink section here, that both encompasses the area or interval in which we are concave down. So -2 to 2, it seems like, right? So I'll write that in as my answer. Maybe I'll highlight it in purple so you can really spot this with me in case you didn't see it earlier. So that kind of greenish, let me just erase what I had earlier so you can see it better. Right, this section right here. It's not exactly the best purple ever, still looks like pink, but it's that section right there. So that right there from -2 to 2 is considered to be concave down. Then now let's talk about what is it? Increasing and concave down. So we're looking for two qualities here, right, that are required, both increasing and concave down. So I'm just going to take a moment and just erase every little color that I have here. So we just focus on increasing and concave down. So the parts that were increasing, let's keep the greens part, I guess, right? It was this section right here, and then this section right here. All right, those are only two sections that were increasing. Ah, I guess I forgot to write down my interval. My bad, guys. Let's fix that. You guys are probably yelling at me to fix that, right? What is it? 4 to 7. Sorry about that. Yeah, we were definitely missing an interval there. So, my bad. All right. So, yeah. Anyways, we're looking for the specific section where we're increasing and concave down. And as for what I've highlighted initially here, it is increasing, but oh wait, that is exactly what I want, right? It's increasing and this section is concave down. So this would be considered to be a valid interval for our answer. The second part that I highlighted, however, definitely not, right? It's increasing, but it's concave up. Hopefully that's straightforward why this interval that I'm looking at right now is not considered to be our solution. So we'll say from -2 to 0 is our solution for part E. -2 to 0. And then the last section, right? Now they're asking us for sections where we're decreasing, but also considered to be concave up. And so luckily enough, let me just re-highlight the sections that we're decreasing so you can see it again. This one I'm highlighting right now is decreasing, but it's not concave up, that's concave down. But then this next little piece that I highlight, right, it might look like one highlighted chunk, but it's a separate one, right? I mean, I'm going to even signify it a little bit more, just this chunk right here, right? Starting at 2 to 4 is where I'm considered to be decreasing and also concave up. Hopefully that made sense, right? If not, slow down the video or ask me in class. Now here's number 2. This one I would say is a slightly harder problem out of what we're doing right now. And so we're asked a graph with a lot of different characteristics that they're describing, right? So I'm going to read it out and we'll try to tackle each piece one at a time, right? It says the graph of k is increasing on the intervals of -4 to 1 and 5 to 7. And k is increasing on the intervals 1 to 5. Additionally, the graph of k is concave up on intervals 3 to 6 and concave down on intervals of -4 to 3 and 6 to 7. Sketch a graph of k using the following grid. And so they kind of just word vomited a whole bunch of info that we have to somehow draw on this graph, right? And then this x and y axis that we have here. I personally like to do this problem one piece at a time. Some people are able to freehand draw this and get it right on the first try. I am not that person. I like to just do one little section at a time to know that I'm doing that part correctly and then just double check it based on, what I have so far. Right? So that's what I'm going to do. But if you are beyond amazing and you could draw it right now without doing all the extra work that I do, great. Okay? But I'll show you how I do it. Right. So let's first focus on the first thing that they described to us. They said that the graph k is increasing on the intervals of -4 to 1 and 5 to 7. So I'm only going to focus on making that part true, right? I'm only going to focus on making this part true for right now. We'll keep adding more. So from -4 to 1, if I had to draw something that's increasing, I mean, simply put, I guess I can draw something like this, right? From -4 to 1, that is considered to be increasing, but I don't know. I don't want to have a graph that kind of looks similar to this, where a majority of it, I would say, is kind of curvy, okay? Because more often than not, that's how they're going to look. And so I might change this just a tad bit instead of a straight line like that. I might just do it, but just a little bit curved, right? More than likely, if it's increasing only there, it's probably going to start decreasing the moment after. So that's probably going to be based on what they're describing here in a second. But I'm just going to keep it like this for right now. And then the other part that's increasing is from 5 to 7. So I might draw something similar. Again, something like that. Right? From 5 to 7, it's increasing. And -4 to 1, it's increasing, right? All those parts are true right now. Then I'll move on to the next part and make sure that they're valid, right? So now it's saying k is decreasing on the intervals of 1 to 5. Well, that makes sense, right? Starting off, what I drew initially was increasing, and it starts to taper off and starts to decrease all the way to 5. So something like that. Something like that. And this looks like kind of a valid graph, right? Looks pretty normal for the most part. And so this part is done. What else is next? Now it's saying additionally, the graph of k is concave up on the intervals of 3 to 6. Let's see, from 3 to 6, it almost looks concave up. Pretty close. So that means I just need to kind of, what's it called? Refine what I have drawn so far. Like for the most part, it looks pretty close to being already correct. So I'm gonna still keep it for sure, almost practically the same, but I really want to emphasize this section from 3 to 6 that I'm concave up. So I might just adjust my drawing just a little bit, right? And keep the prior things to still be true, but really just emphasize that, well, from 3 to 6, we are considered to be concave up. And that looks a lot better now, right? I'm just kind of refining my sketch based on the additional information while keeping all the prior things true, right? For sure, still from 1 to 5, I'm still decreasing very much, right? It's still very much decreasing, albeit it looks a little bit ugly. Maybe I can adjust it even some more if I was so picky about this to make it look nice. All right, that looks a little bit better. I could try again and connect it. And come on, there we go. Perfect. All right, and let's see what the last thing they say. All right, it says concave down on the intervals of -4 to 3 and 6 to 7. So we're just double checking that my graph is concave down on those intervals. So let's say -4 to 3, it is for sure concave down. From 6 to 7, almost quite there, just based on what we've drawn so far. Maybe I'll just add a little bit more to it, like this, to really emphasize that, right? Maybe from 6 to 7, right? So maybe something like this. Maybe something like that. And that's about it for that problem. So again, this is the way I interpret it. If you have a totally faster way of doing it, feel free to do so. All right, here's number 3. They're giving us a table here. It says the table lists the life expectancy of U.S. females born in a given year. Find the average rate of change in the life expectancy of U.S. females born from 1850 to 2000. Include units of measure. Okay. So they gave this table in different variables. Not that it changes the problems at all, but essentially this is basically our x, and this is our f of x. They just named it differently with different letters, right? And so I think all they're asking us to do is just find average rate of change, right? That's all that's being said here. And we know that formula based on what we learned last class. I'm going to rewrite that formula down again. y2 minus y1 over x2 minus x1. And so they want it from 1850 to 2000. So here's my x1, here's my x2, here's my y1, here's my y2. So I have everything I need to plug into this equation. So let's plug it in. I have 81.83 minus, that's not right. Oh, that is right. 46.10, all divided by 2000 minus 1850. And I'll probably just use my calculator here to reduce this. But here, give me 1 second. I'm using my calculator now. All right, I should be back. I finally calculated it. Right. After putting it into the calculator, I got 0.2382. Right. Uh, and I should also include the unit of measure. In this case, well, what is it? Average round trip life expectancy. Well, it shouldn't just be age in years, right? I guess I could do that, right? Can you even do that in slope? I'm gonna avoid it. That doesn't feel right. I'm just gonna write the number, right? Include units of measure. Not sure if it has one when you're writing slope, but anyways, I'll change my mind if I figure that out. Now here's instantaneous rate of change. As far as this goes, um, let's just fill out the missing blanks that we have here, right? So the idea of instantaneous rate of change is equivalent to find the rate of change. So same thing, just different name, right? Of a function at a given point. This concept is developed formally and used in calculus, but we can approximate the rate of change at a point by using the average rate of change, right? Average rate of change formula over smaller intervals. Right? The smaller your interval, the more instantaneous that it occurs, right? So if I say from 1 to 5, that's a fairly large interval, right? But if I reduce it to one of the examples that we have here already, 1 to 1.1, right? In terms of time, well, not much time has really elapsed from 1 to 1.1. So we're trying to figure out the exact slope at a very specific instant part of time, essentially, right? And I've already kind of filled out this section. We're kind of just practicing average rate of change again. So if you kind of want to just practice it and see if we have the same things, feel free to do so, or simply just write down some of the work that I have here, right? But I pretty much just used the formula here that they already provided to us and plugged in our intervals, right? You should have done this in our homework prior. And they did provide us a domain restriction. Not that it really mattered too much in this problem. But really, we're kind of just evaluating the average rate of change between all these intervals. And you can see that it starts fairly small, right? 1 to 1.1, and then 1 to 1.01, right? The interval got even smaller. And the average rate of change that went from the first one was, well, 14.71 to about, what was it, 15.151. So that rate of change got even larger, right? So it seems like it already tapered off pretty quickly, this ball that you throw vertically in the air. And then as we get even smaller intervals, right? Now we're going from 1 to 1.001, right? This is, what is it? Tenth, what is it? Thousandth of a second now, right? The slope now is 15.19, 1951, right? And then we go even the other way, right? Now we're doing a thousandth of a second prior to 1, right? We're going from 0.9921, and our slope in this case is 15.2049. And so with all this info in hand, we can kind of make an assumption about what occurs exactly at 1, right? And so that's what part E is asking us, right? Is this based on the answers above, what do you think is the true rate of change in the height of the ball at t equals 1 second? So we've done all this extra work, essentially, seeing what happens prior to 1 second and what happens after 1 second with very little difference in our intervals, right? Not much change, right? Um, and you can see as we kind of hone in on 1 second from both sides, right, that these last two answers are the best ones to use to really interpret this, right? The first answer on the left here that I'm going to point out, right, that's a little bit after 1 second, and this was a little bit before 1 second. And you can see that we're kind of approaching the similar number, which is about 15.2. So I'm just estimating here, of course. I genuinely don't know what's happening at exactly 1 second, but I can make a pretty decent assumption that's what's going to happen, right? It's about 15.2. 15.2 uh, is the slope, right? That's just the true change in height at that time. And I could justify the response just based on what I said, right? We checked both sides of the intervals, and we just kind of got closer to 1 as much as we could, and we just estimated it from there, okay? So that's the answer for that. Now on this last section, if you can give it a shot before I do it, that would be cool, just to see what you get. These are not exactly tricky per se, but maybe I can correct your way of thinking if you did do it wrong, right? So pause here, try it out, and we can do it together. So let's see. It says for each scenario below, determine whether the two quantities typically have a positive rate of change or a negative rate of change. Okay, easy enough. So part A is saying, well, if you have a situation where a child's age and the child's height, well, typically a normal person who grows up over time, they tend to increase in height. So if I was to label an x and y axis here and say that this was the age, maybe I'll center it. Oops. Let's just write it again, age, and say that this is height. Well, I would say over time, as you get older, you do increase in height. After a certain point, you might taper off completely, but that's not really the behavior that we're looking for. Overall, at the beginning, you do grow in height, right? Unless you have very substantial circumstances. So I would say for part A, you would have a positive rate of change. Here's part B, a golfer's skill level and the golfer's score. My understanding of golf is that you want to do the less, or sorry, not the less, the least amount of strokes, right? The least amount of swings on a course. That shows how good you are, right? When you finally get it in the hole, right? With the least amount of strokes. And so when it comes to scoring, you want to score the least essentially. So if I was to still label my x and y axis and say that this is the skill and say that this is the score of the golfer, well, if they have a high score, they must have very much no skill. So I'd probably start up here. And then as I increase in skill, I'm probably swinging a lot less to get it into the hole. And so you end up approaching it like that. I mean, for sure, I would imagine this line even goes even under here because I think you can have a negative score in golf. I don't play golf if you couldn't tell, but I'm pretty sure that's true. So in this case, based on the graph alone, I can see that we have a negative slope or perhaps a negative rate of change. And then our last one, right, part C. The height from the ground of a coin dropped off the Burj Khalifa and the speed of the coin. As far as what this place is, I think I looked it up. It's just a really tall building somewhere. I forgot where exactly. So let's label our x and y axis. Right. Simply put, the simple answer is just that, well, it has a negative slope. Okay, and I'll kind of go more in depth in this in here in a second, if this is not enough for you. All right, so let's just say for some reason the speed of the coin is here, and this is the height, right? And so when you start at a high height, it might be easier if I draw it again, but start from over here, right? If I start from a high, very high height, starting off initially, I should increase in speed, right? Increase in speed like this until I hit my terminal velocity. If I really want to be really accurate with this depiction, right? Again, this is still height, and this is still speed. Then I would very much still start here, right? I'll reach my terminal velocity, and then we'll kind of hit this terminal velocity for a while until we reach the ground, basically. All right, so I'll keep going, and the moment I'm about to hit the ground, well, obviously the coin has stopped moving, right? So there's no more speed to it the moment it hits zero. So that's our accurate representation of the whole duration of the coin traveling. However, the main priority that we're kind of looking at is this initial behavior here, right? So that's why I'm saying that, well, in general, we have a negative rate of change. If you really wanted to, for some reason, really examine this spot right here and had a really, I don't know, zoomed in look, it's not exactly a positive slope since it pretty much just hits the ground. It goes from 100 to 0, basically. So there's not much to interpret there. But I thought I'd explain it anyways. Well, that's it. I've been talking for 26 minutes now. Thank you for watching. And if you made it this far, have a good day. Thank you for being here. And I'll see you sometime soon. Bye.